Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of a unit waves. So let's begin with today's class. In today's class, first we are going to discuss about the reflection of a waves. So let's begin. We can say that when waves are incident on a boundary between the two media, a part of incident wave returns to the initial medium, that is what we call as a reflection, and while the remaining part is partly absorbed and partly transmitted into the second medium, this is what we call as a refraction. As you can see that there are two different waves, or as you can see that there are two different mediums. First wire is very thin wire, another wire is very thick wire. This is the first one and this will be the second one. So as you can see that a certain wire, a certain wave is reflected back, while the certain wave is transmitted and refracted. So let's discuss the reflection of wave pulse from a rigid boundary. Basically, we are going to discuss a two situation. One of them is the rigid reflection with the rigid situation, and another is the reflection with the free surfaces. So this is the first case. As you can see that the string is fixed at its right end, and when the pulse arrive from this, it's when the pulse arrive at that end, it exerts an upward force on the support at the wall. So now according to the Newton's third law, this support exerts an equal but opposite force on the string, and if this provides equal but opposite force on the string, then this reaction force generates a pulse at the support which travels back along the string, and there is a result in a phase change of pi radian. As you can see this, a pulse has been generated from here, and as you can see this, if pulse has been generated from here, initially incident pulse is going in the positive x direction. So if I write down the relation for the positive x direction moving wave, it's a yi, it's a sine, let's say omega t minus of k into x. But when this is reflected back, it is look something like this. This is yr, which is equals to a sine. As it is moving in negative x direction, this is omega t plus kx, and there is a phase there is a phase difference of pi 2. It's omega t plus kx plus pi. So this is the reflected wave having the phase difference of pi. I hope this is clear. Is it clear? Is it? Are you sure? So do you have any doubts in this up till now? Now let's look at the case of the free end. That when the incident pulse arrives, the ring moves up the road, and there is no phase change. There is no phase change between the incident and the reflected pulse. So basically, as the ring moves, it pulls on the string, stretching the string and produces a reflected pulse. And this reflected pulse is moving with the same amplitude as the incident pulse. So basically it is the same thing, that when you move with the yi, that is equals to a sine omega t minus of kx, and the reflected wave for the same would be equals to a sine omega t plus kx. So this is the case, and there is no phase difference because as you see this, that however it has arrived, it is moving in the same direction with the back. I hope this is clear. Is it clear? Is it? Do you understand this? Are you? Great. So basically when we discuss this two things, that we have a reflection we have a reflection from two rigid surfaces. One of them is the rigid surface, and another is the free surface. So one of them is the rigid surface, another is the free surface. When we talk about the transverse waves, with the rigid surface there is a phase difference of pi, and with the free surface there is a phase difference of 0 degree. When we talk about the longitudinal wave, a situation exactly reverse. When we talk about the longitudinal wave, the situation will be reversed, and for the rigid surface its phase difference is 0 degree, and for the free surface its phase difference is pi degree. So this will be the situation. I hope this is clear. Is it clear? Is it? Great. So let's have a look to certain quick questions. The question says, when the incident wave is reflected from the fixed end, the phase change between the incident and reflected waves is blank radian. Yes, from the fixed end, the phase difference it's a pi degree. Next, when the incident wave is reflected from the free end, the phase change between the incident and the reflected wave is, yes, it's a free end, then this will be the 0 degree. I hope this is clear. So can you do this kind of questions based on the reflection of a wave? Can it be done? Can it be? Are you sure? Great. Now let's look at the next topic, and that is about the beats of a wave. So let's begin with beats. Now what is beats is all about? Let's have a look. So let's suppose this are the two tuning forks. They are of same frequency, sounded together. The resultant sound, that is what we are going to hear, is the superposition of these two waves, and they will be in the same frequency of either tuning fork, but it would be of greater intensity. I hope this is clear, that when let's say this is the having the frequency f, this is having the frequency f, and when this two sounded together, that the frequency we heard is one of them too, because both would be of same frequency, both are tuning with the same frequency, but the resulting intensity would be the greater one. Yes, I hope this is clear. So if one of the fork is slightly loaded with little wax on one of its prongs, and if both are sounded together, once again, that's let's apply a little wax over one of the prongs, then the intensity of the resultant sound varies at a regular interval of time, and this is the bits is about the phenomenon of two sound waves of slightly different frequencies traveling in same direction superimposed together. Then the intensity of resultant sound wax and wanes at regular intervals of time, and this waxing and waning of the sound wave is what we call as a bit. So basically it's in the amplitude of the resultant wave that gradually increases to maximum, that is what we call as a waxing, and it decreases to minimum, which is what we call as a waning, regularly with the time. This rise and fall of the sound intensity, at regular interval is what we call as a bits. I hope this is clear. So let's look at this. One waxing and waning of the amplitude constitutes a bit, and the number of beats occurring per second is known as the beat frequency. Beat frequency is always equal to the difference in the frequencies of the two interfering waves. So we can say this is delta n, which is equals to n1 minus n2, and this where delta n it's a bits frequency, and n1 it's the frequency of first tuning fork, and n2 it is the frequency of the second tuning fork. So this will be the n1, this will be the n2. Yes, and their difference will be equals to delta f, which is equals to f1 minus f2. Great. Now let's derive the expression for the beat frequency. Let's suppose consider that the two sound waves of same amplitude but of slightly different frequencies n1 and n2 are moving in the same direction, and let's suppose at x equals to 0. Yes, basically when we described the wave, it was y is equals to a sine omega t minus of k into x, and at position x equals to 0, we can write this, that this is equals to a sine omega t. So this is y1, which is equals to a sine omega 1 t, and that stands to y1 is equals to a sine 2 pi n1 into t. Another one is the y2, which is equals to a sine omega 2 into t, which is equals to a sine 2 pi n2 into t. And according to the principle of superposition, when I superpose this two, it would be equals to y, which is equals to y1 plus y2. So when it is equals to y, which is equals to y1 plus y2, I can have this, it's a y which is equals to a sine omega 1t plus a sine omega 2t, and that would be equals to a into bracket sine omega 1t plus sine omega 2t. This is equals to a sine 2 pi n1t plus sine 2 pi n2t. So this is equals to a into bracket 2 sine and the bracket 2 pi n1 plus 2 pi n2 by 2 into cos 2 pi n1 minus 2 pi n2 by t, and this is equals to 2a sine 2 pi into bracket n1 plus n2 by 2 into t into bracket cos of 2 pi n1 minus n2 by 2 into t. So if I simplify this, then this term is the amplitude and the remaining term is the frequency. So this is what we call as an a dash sine 2 pi n1 plus n2 by 2 into t, and here a dash, this is the amplitude of the resultant wave, and the resulting wave frequency will be n1 plus n2 by 2. Now you can see that this is the frequency with which amplitude do changes. I hope you understand this. Yes, that this is the frequency with which amplitude changes, and when amplitude changes with the frequency of n1 minus n2 divide by 2, when the amplitude changes with n1 minus n2 divide by 2, that means if both the tuning fork are being tuned with different frequencies, that means they will oscillate, that once it would be an waxing, another it would be a waning, and their amplitude will keep on changing, as you can see this. Let's have a look. Yes, as you observe to the amplitude of a wave, that when two waves are combined having difference in their frequency, again this difference is very little but it would be there, then you can see the amplitude of the resulting wave. Yes, it keeps on changing. One time it's a maximum, another time it's a minimum, one time maximum, minimum, and so on. So this is what beats is all about. I hope this is clear. I also request you guys to please note down this frequency with which the amplitude varies and the frequency with which wave frequency varies. Yes, have you noted it? Did you noted it? Great. So this is maximum. This is maximum when cos of 2 pi into bracket n1 minus n2 by 2 into t would be equals to plus minus 1, and if it is equals to plus minus 1, then this is equals to plus minus 1 will be equals to cos of n pi. So if I took an inverse ratio on inverse function on both the sides, it's a 2 pi into bracket n1 minus n2 by 2 into t, which is equals to n pi. Pi has cancelled, and this 2 cancel. So this is n1 minus n2 into t, which is equals to 1. So this is equals to t, which is equals to n divided by n1 minus n2. So if n equals to 0, this t naught equals to 0. If n equals to 1, this is equals to 1 upon n1 minus n2. When n equals to 2, then this t2 will be equals to 2 upon n1 minus n2 and onwards. So when n equals to n, this tn would be equals to n upon n1 minus n2. I hope this is clear. Is it? Is it clear? Are you sure? Do you have any doubts? Is there anything? No? Great. So this t1 minus t naught, or that should be equals to t2 minus t1, or it would be go on, would be equals to 1 upon n1 minus n2. And this delta t, this change in the time, would be equals to 1 by n1 minus n2, or this is change in frequency, which is given as n1 minus n2 when n1 is greater than n2. So what we understand, it's beats of frequency. The beats frequency would be equals to the n1 minus n2. I hope this is clear. So now, do you have any doubts? Is there any doubts? Do you have any doubts? Is there anything? No? Great. Let's move on. Let's discuss the uses of the bits. We are using the bits to determine the unknown frequency, of the tuning fork, to tune a musical instrument, to give an a note, to detect the poisonous gases in the mines, and to produce the special effects in cinematography. We are using the bits. I hope this is clear. Great. So now let's begin the question answers of the bits. Let's look at the first question. It says that the speed of the sound wave in a gas in which two waves of wavelength, which is 1 meter and 1.02 meter, produces 6 bits per second is, that means speed of the sound wave is required. Okay, so what we are supposed to do is that delta f would be equals to f1 minus f2, and as they have mentioned, they produces a 6 bits per second, so this is 6. Now when we say it's a speed of the sound wave in a gas, that means it's a v is equals to f lambda case. Yes, so when I say f, it would be equals to v by lambda. So this will be the f would be equals to v by lambda, and this is equals to v by lambda 2 minus v by lambda 1. Let's write this as an f2 minus of f1. So this is equals to 6, which is v, into 1 by lambda 2. It's a 1 by 1 minus 1 by 1.02. I hope this is clear. Yes, so this is equals to v into bracket 1.02 minus 1 divided by 1 into 1.02. This is equals to 6. If you are going to solve this, you will find this. I hope this is clear. Is it clear? Any doubts? Is there anything? No? Great. Let's move on to the next question. Tuning fork X of frequency 258 Hz gives 8 beats per second with tuning fork Y. Okay, so we are having two tuning forks. One of them is the X, one of them is the Y, and this tuning fork X is having a frequency of 258 Hz. Okay, and it gives 8 bits per second with tuning fork of Y. Okay. When this is 258, either it could be a two option. Either this Y would be of 250 Hz, or it is a 258 plus 8, which is 266 Hz. So either of these options will be available, that either it would be of 250 hertz or it would be of 266 hertz. One of this would be possible. Now, when we say it is when y prongs are cut a little and they are sounded again. Okay, so when I'm going to cut the prongs of the y, yes, when we are going to cut the prongs of the y a little, that means their inertia is reducing. And if their inertia is reducing, that means their frequency would be little higher. That means if a correct answer would be 250, it could be, let's look at this. This is the x, which is 258, and this was the y. Either of this two would be an option, would be an answer for sure. It's a 255 or 260, 250 or 266. Now, as I am reducing the inertia of this will start increasing. That means it could be 252, 254, 256 or 258. Let's check with this also, that if this frequency starts increasing, this could be a 268, 270, 272, 274 and onwards. Yes, so this can occur. Now what they says, that when they are sounded again, the number of beats remain the same. Okay, so number of beats should remain the same. It should be an 8. So when initially it was, this was at a 258 hertz, and initially let's say this is 250 hertz, the number of beats were the 8. If this starts increasing, 250 starts increasing, and it will keep on going, it can reach somewhere at 266 hertz. But if this will start increasing, this will go beyond 266. That means with this you are not going to receive 8 bits per second again anytime. This is simply not possible. But with this is the possible. So the correct frequency of this wide unknown frequency is the 250 hertz. I hope you understand this. Yes, always use trial error approach. This is the best possible approach. This trial error approach is best possible approach in the questions based on the views. So you can always go for it. This will give you a correct result within a no time. Yes. Next, let's have a look. They said that the two tuning forks A and B give 6 bits per second and are resonates with a closed column of air which is 15 centimeter along, and B is there with an open column of air which is 30.5 centimeter along in their fundamental harmonics, and we need to find out their frequencies. So how should we do this? As you understand that there are two tuning forks, one is the A, this one would be the B, and they will give the 6 bits per second, and A resonates with a closed column. So when we talk about the closed column, this is equals to V by 4L, and when we talk about the open column, this is equals to V by 2L. I hope this is clear. Is it clear? Is it? So basically it is the situation that bits frequency f, which is equals to f1 minus of f2. The number of bits, it was the 6, and that is equals to v divided by closed column length. It's a 4 into 15 minus of v divided by 2 into open column length. This is equals to 30.5. So this is equals to 6, which is equals to v by 6060 minus v divided by 2 into 30.5, which is 61. Yes, so this is 6 is equals to v into bracket 61 minus of 60 divided by 6060 into 61. I hope this is clear. So this 6 is equals to v into bracket 61 minus 60, this is equals to 1, divide by 60 into 61. So this v would be equals to 6 into 60 into 61, and if I put up the value in this any relation, then I can get the NA and NB. It's two frequencies. I hope this is clear. Is it clear? Is it? Are you sure? Great. So now, are you ready for the next questions? Are you? Great. So let's begin with the questions. Let's suppose if if two sound waves the y1 is given as it is equals to 0.3 sine 596 pi into bracket t minus of x by 330, and the different wave which is equals to y2 which is equals to 0.5 sine 604 pi into bracket t minus of x divided by 330 are superposed. These two are the superposed. What will be the first frequency of resultant wave, second frequency at which amplitude of resultant wave varies. Next, it's a frequency at which beats are produced, and next it would be the ratio of maximum and minimum intensity. So this is all what we required, that they have given the sound wave and they are having the y1 is given, y2 is given, and these two waves are superposed with each other. We need to find out that what will be the frequency of the resultant wave and the frequency at which amplitude of the resultant wave varies and the frequency at which beats are produced and the ratio of the maximum and minimum intensities. So how will we do this? Whatever the relation I have been given, let's see them again. It's a y1 which is equals to 0.3 into sine of 596 pi into bracket t minus x by 330, and this is the y2 which is equals to 0.5 sine, it's a 604 pi into bracket t minus x divided by 330. So the omega 1 it's a 596 pi, and the omega 2 which is equals to 604 pi, and the a1 which is equals to 0.3 and a2 which is equals to 0.5. So as omega 1 is given, their frequency is would be available. It's a frequency 1 would be equals to 298 hertz, and the frequency 2 it's a 302 hertz. So this is frequency 1 and this is frequency 2, as well as we have been given the a1 and a2 which is equals to 0.3 and 0.5. So first it's a frequency It's a frequency of resultant wave is required, so it's a frequency f dash would be equals to f1 plus f2 by 2. This will be the f1 plus f2 by 2. This is equals to 298 plus 302 divided by 2, which is equals to 300 hertz. Yes, is that clear? So this f dash, that should be is equals to f1 plus f2 by 2, and this is equals to 298 plus 302 by 2, which tends to 300 hertz. Next, it is the frequency at which resulting amplitude varies. So basically it's an f dash which is equals to f1 minus f2 divided by 2. And when I say it's an f1 minus f2 by 2, this is equals to 302 minus of 298 divided by 2, which tends to this is 300 minus 298, 2 by 2, it's 1 hertz. It is the frequency with which it varies. I hope this is clear. Is it clear? Is it clear? Is it great? Now next frequency at which beats are produced. So beats frequency it's a 2 into f1 minus f2 by 2. So this has gone, and this is equals to f1 minus f2. This is simply the 2 hertz. I hope this is clear. Yes, yes, no. So the data was 302 hertz and 298 hertz. Sorry, I made a mistake over here. So it's a 4 by 2, which is equals to a 2 hertz. And this will be the 4 hertz. Yes, now it is clear. Great. Now next, what do we need to find out? We need to find out the ratio of the maximum and minimum intensity. So it's an Imax is to I mean. That is what we require. It's Imax to the I mean, which is equals to this Imax is to I mean, which is equals to A1 plus A2 whole square divided by A1 minus A2 whole square. I hope this is clear. So this is equals to 0.3 plus 0.5 whole square divided by 0.3 minus of 0.5 whole square, which tends to this is equals to 0.8 whole square, which is 64, and this is 0.3 minus 0.5, it's a 0.2. That means if I make a square of this, it's a 4. This is equals to 16. I hope this is clear. Is it clear? Is it? Are you sure? Great. Let's look at this question. The question says, what is the bit frequency? What is the bit frequency when two waves of frequency which is 450 hertz and 456 hertz are superposed. So when I want beats frequency is to be done, it's a mode of f1 minus f2, which is equals to 456 minus of 450. This is equals to 6 hertz. I hope this is clear. Now let's suppose I have been given that with what frequency wave frequency changes. So that could be given as f1 plus f2 divided by 2, and this tends to it's a 456 plus 450 divided by 2. So basically this is 450. This is 450. Divide by 2, it's a 453. Yes, I'm taking directly the difference and add it. So this is equals to 453 hertz. I hope this is clear. Is it clear? Is it? Great. Ready for next question? Let's have a look. The question says that a tuning fork produces 3 bits per second when sounded together with a fork of frequency 364 hertz. When the first fork is loaded with little wax when first fork is loaded with little wax, then the number of beats becomes 2 per second. What is the frequency of first fork? So this is the question. How will you do this? First go through it carefully. They mentioned it that the tuning fork is there and it will produce 3 bits per second when it's sounded together with a fork of frequency. This is of 364 hertz. So basically we are having two forks. One, it's a value of 364 hertz and the other we don't know. Okay, so let's begin our discussion that this was the two forks. This is X, this is Y, and this is of 364 hertz, but it is producing 3 bits per second with this. So when it produces 3 bits, that means either this could be of 367 hertz, which is 364 plus 3, and either it could be of 361 hertz. So either of this would be the answer for sure, that either it could be a 367 hertz or it could be a 361 hertz. Now, so when the first fork is loaded with little wax, so this is the first fork, that is, then the number of beats becomes 2 per second. Okay, great. So this is the first fork, this will be the second fork. When this is going to be loaded with the wax, so if it is going to be loaded with wax, that means inertia increases, and if inertia increases, that means frequency will decrease. So if frequency decreases, this is 364 hertz, then it could be moved to the 362 either, or 360 or 358 or 356 or something like that. So now when it has been loaded with the wax, the number of beats per second will become a 2. So if this has been number of beats per second will become 2, how this will be the possible? Yes, when this is possible. So if this has been loaded with the wax, give me a moment and look at the data one more time. So what is the frequency of the first fork? Yes, this is what required. How will you do this? Yes, so if you check with the 367 hertz, if you check it with the 367 hertz, it is keep on going. Yes, but with 361, here 359 could be there, and this can give a 2 bits per second. I hope this is clear. So if this can give 2 bits per second, that means this could be the correct answer. That means this tuning fork will be having the frequency, the unknown frequency what we are finding out is 361 hertz. I hope it is clear. Is it? Is it? Are you sure? Great. Now let's look at the next question. This question says that a string under a tension of 129.6 Newton produces 10 bits per second when when it is vibrated when it is vibrated along with tuning fork. When the tension in the string when the tension in the string is increased to 160, it's a 160 Newton, it sounds in unison with with the same tuning fork. Calculate the fundamental frequency. Calculate the fundamental frequency of the tuning fork. So a string is given and that is under a tension of 129.6 Newton, and this is, let's say this was initial tension which is 129.6 Newton. It produces 10 bits per second when it is vibrated along with a tuning fork. So there is a certain string is vibrating as well as tuning fork is vibrating, and this is, let's say F1, this is, let's say F2. This F1 minus F2 will give me the 10 bits per second. It could be a plus minus 10. Okay, great. Next, so when the tension in the string is increased to 160 Newton. Okay, great. So next tension T2, it's a 160 Newton. As this has been increased, it sounds in unison, that means with the same frequency, with the same tuning fork. So calculate, they said calculate the fundamental frequency of the tuning fork. Okay, so what we understood is that F is equals to N into V by 2L, and when I say it's a V by 2L, it's a 1 by 2L under root of T by mu. So basically this is frequency directly proportional to the root of T. I hope this is clear. So if I took the delta F, if I took the delta F by F, and this could be equals to the N minus 10 frequencies divide by N, that would be equals to root of it's a 129.6 Newton divide by this frequency, that means it was the 160 Hertz. I hope this is clear. Yes, so when it was producing 10 bits, its tension was 129.6 Newton, and when it is having the frequency as an n, it is having the tension as a 160 because it is in unison. So if I solve this, you will find this n would be equals to 100 hertz, and that's it. You did it. Great job. I hope this is clear. Was it clear? Was it? Are you sure? Are you? Do you have any doubts? Is there anything? No? Great. Now we want to discuss certain more aspect with intensity. Let's have a look. So when we discuss intensity, we have different kind of source. One of them is the point source. So it is just like a dot. You can see that, or you can assume that there is a bulb in the room and it is at the center part of the room. So whatever the energy or whatever the response that bulb get received when you switch on the bulb, that it will deliver the energy in one of the spheres. Yes, this one will be the sphere having radius r. And if you are at this end, what energy or what intensity you are receiving, it is basically intensity is equals to energy divided by area into time. I hope this is clear. So basically this is intensity is energy divided by area, which is equals to 4 pi r square into time. As you will and your friend is at here, so this distance, let's call this as an r1, this as an r2. So your friend definitely will receive a later amount of energy because this intensity I is inversely proportional to the r square. This is the case of the point source, where intensity is decreases with a relation of 1 by r square. I hope this is clear. Now let's talk about that it was the second source, and that would be the, let's say, line source, something like this, that from here the energy will be moving. So then it will form a certain cylinders having length L, and this is the radius r. So again intensity is equals to energy divided by area into time, and when it is intensity is equals to energy divided by area into time, this will be equals to E divided by area, which is equals to 2 pi r into L into T. So this intensity is inversely proportional to the R. I hope this is clear. This is I, which is inversely proportional to the 1 by R. So do you have any doubts? Is there anything? Is there? No? Are you clear with this? Are you clear with this? Any doubts? Is there anything? No? One more thing, that when we say that intensity is directly proportional to the r square, we also know that intensity directly proportional to the a square. So it is basically in a square directly proportional to the 1 by r square for the point source. So for the point source, it's a 1 by r. A amplitude A is directly proportional to the 1 by r. So at this point, it is inversely proportional to the distance. And here, it is a square directly proportional to the 1 by r for a line source, and that is a directly proportional to the 1 by root of r. I hope this is clear. Is it clear? Is it? So do you have any doubts in this? Any doubts in this? Are you sure? Do you understand this? Are you clear with this? Are you? Any doubts? Is there anything? No? Great. Now let's discuss what is loudness. What is loudness of sound? So amplitude of wave is measure of loudness of sound, and loudness of sound is measured in decibel, and its formula is L is equals to 10 log 10 I by I naught, where I naught is the threshold intensity, which is equals to 10 to the power minus of 12 volt per meter square, and I is the intensity of sound wave. So I is the intensity of sound wave, and I naught, it is the threshold intensity of sound wave, and this is the loudness of the sound. I hope this is clear. Is it clear? Is it? Are you sure? So do you have any doubts up till now? Is there anything? No? Great. So are you ready for question based on the loudness? Let's suppose the question says that, suppose a y1 is given, which is equals to 10 sine 20 pi x minus 40 pi t. Y2 is given, which is equals to 5 sine 20 pi x minus 40 pi t. Find out difference of loudness for the given wave. So this is L1. This L1 could be given as 10 log to the base 10. It is I1 is to I naught. This L2, it's a 10 log 10 I2 is to I naught. Yes. So basically what I want the intensity, and I must understand that this intensity is directly proportional to the A square. So this I1 is to I2, because both are having the frequencies same. So this I1 is to I2, this is equals to 100 divided by 25, which is equals to 4 is to 1. So this is I1 is to I2, which is 100 is to 25, which is equals to 4 is to 1. So let's differentiate. It's an L2 minus of L1, which is equals to 10 log of 10. This is I2 to the I naught multiplied by I naught to the I1. So this I naught has been cancelled, and this will be the 10 log I2 is to I1 to the base 10. This is 10 log 10. I2 is to I1, it is, or I1 is to I2. This is I1 is to I2. Okay, so let's change this as an L1 minus L2. This will be the I1 is to I0, I2 is to I0. Yes, this is the I1, this is I2. So this is equals to 4 is to 1, and this seems to, this is 10 log 10 2 square. So this is equals to 20 into log of 2 to the base 10. Log 2, it's a 0.31. Yes, so it's a 20 into 0.3, and this would be the answer in dB. I hope this is clear. So now will you be able to do this kind of questions? Will you be? Are you sure? Are you? Great. So let's wind up the session over here. This was all about the beats, and we have also discussed the reflection of wave as well as the intensity and the loudness. So please do this kind of questions. Please revise it thoroughly. This will help you to get the good numbers. Thank you. Have a good day. Take care.